Okay, we're going to get started. I want to go through the slides for chapter 7 with you in the hopes that you will actually look at this yourself before class on Wednesday or Thursday, so that then in class you're prepared to ask questions. I think a lot of this should be review for you, so just taking a little look. And I know this is kind of hard to see through the swivel, but just know that the PowerPoint for this is posted on Schoology, so you can pull up the slides and look at them on one device while you watch the video. Okay. You've studied last year in chemistry about the development of the periodic table. You know that Mendeleev is considered to be like the father of the modern periodic table. There was another guy who also came to that same conclusion at about the same time. And the big deal about both of them was that they understood how to group elements by properties. Okay? As you know, the elements on the periodic table go in order of atomic number at this point. It used to go in order of atomic mass, which mostly works because atomic number and atomic mass are almost perfectly in order. However, there are a couple elements that have some discrepancies. Okay, so for example, I think argon and potassium are examples. Argon is slightly heavier than potassium, even though it's number 18, and potassium's number 19. Okay, so in their day, they put them in order of atomic mass, but that's because atomic number, keep in mind, like with these guys, this was in the mid-1800s, the solid sphere model was the model of the atom that predominated, okay? They didn't even know about electrons. They definitely didn't know about the nucleus. They didn't know about protons. So all of those aspects of elements didn't exist at that point in time. So when they came up with the idea of atomic mass, that was actually a really great idea for what they knew. And it was the only organizing principle that they could really have because the other ones weren't known to exist yet. So they put them in order of atomic mass, which again, pretty much worked perfectly until we discovered atomic number, and then we just flip-flopped a couple things around. However, the thing they did that was even more brilliant was that they understood, like instead of just making one long continuous row, they understood that when properties started to repeat themselves, to make columns, okay? So one of the things that these guys did was they grouped them in columns according to similar properties, which is why, for example, all of the alkali metals are highly reactive elements, okay? Because they knew to group them that way. What really made Mendeleev stand out, and probably is why he gets credit for the periodic table, is that he didn't just come up with the idea of grouping them by similar properties and atomic masses. He understood his categories so well that there were certain places on the periodic table where they didn't know elements would fit. And what Mendeleev did was he made predictions for properties for elements that had yet to be discovered. The classic example of that is germanium, okay, where germanium had not yet been discovered in the time that Mendeleev came up with his periodic table. He came up with his in 1871. Germanium wasn't found until 1886, okay, but because Mendeleev understood his organization pattern so well, instead of forcing an element to fit in there under silicon, he left that spot blank and he wrote a list of properties that he thought there would eventually be an element discovered that would have these properties. So for example, he said like it's going to weigh about 72, it's going to have a density of about 5.5, it's going to look like this, it's going to bond in these proportions, it's going to have this boiling point. Okay, and then they discovered germanium, and lo and behold, his properties were pretty much spot on. Okay, So that was really what made Mendeleev stand out, is because he was able to actually predict the properties of elements that hadn't been discovered yet and say where those undiscovered elements would end up going on the periodic table. And then when we discovered them, it turns out he was really right, okay? But keep in mind that after Mendeleev's time, a lot of progress was made on the atomic model. So we went from Dalton's solid sphere, which is really what Mendeleev knew at the time, to J.J. Thomson finding that there were electrons in the atom. And then a few years later, Rutherford discovered there was a positively charged nucleus, and the electrons were around that nucleus. And then shortly after, they found the proton, they found the neutron, and they really started to understand what the atom was made of. So then, instead of organizing by mass, somebody named Henry Moseley came in and just said, I think we should use this atomic number instead, which was based on the number of protons. And then they put them in order of atomic number. And like I said, there are a few elements that go in order of atomic number, but their masses are not in order, okay? But that's no big deal, because that's just based on isotopes. All right, so periodicity, which is really what this chapter is about, and this should be a lot of review for you, is the idea that there's a repetitive pattern of a property based on atomic number, okay? So again, the alkali metals, okay? They all have similar properties. They are highly reactive elements. They're very soft. They're dull looking, okay? And that's an example of a periodic property, which is why they go in order, okay? As you know, the alkali metals all have one valence electron, all right? We're going to focus on these properties, okay? We're going to focus on the size of atoms and ions, ionization energy, electron affinity, and some of the properties of specific groups, okay? We also need to go back to this concept of nuclear charge, which we discussed in Unit 1, although we didn't really use this term that much, okay? All right, nuclear charge. Nuclear charge is one of those terms that, just so you know, on the AP test, they would want you to very specifically use the term effective nuclear charge, okay? So don't describe it, don't dance around it, don't say something that sounds like it. Be very, very specific and incorporate that phrase, effective nuclear charge, into your chemistry vocabulary, okay? Ultimately, what this means is there is attraction between the nucleus and the electrons. And that attraction depends on how many protons are in the nucleus, because as you know, the protons are positive and electrons are negative, and there's attraction between those protons and those electrons. However, there are other electrons floating out there, and those electrons get in the way of some of the electrons. And what happens is they kind of shield other electrons from the nucleus, okay? So the forces that an electron experiences depends both on how attracted it is to the nucleus and how successfully it's repelled by other electrons, okay? There's technically a formula you can use for this. I think it looks a lot more complicated than it really needs to be, okay? So what you can say is that the effective nuclear charge is basically the atomic number, okay, minus S, which they're going to call a screening constant, but really like the cheap way to do it, the quick and easy way to do it is just, instead of calling it a screening constant, let's just say it's equal to the number of core electrons, okay? So for example, sodium, its atomic number 11, okay? You know sodium's configuration is 1s2, 2s2, 2p6, 3s1. Well, 11 minus 10 gives it an effective nuclear charge of 1. Why minus 10? because when you listen to that configuration again, 1s2, 2s2, 2p6, now we're up to 10 core electrons, and then 3s1 is the valence electron. So 11 minus 10, because it's the atomic number, minus the core electrons, is your effective nuclear charge, which is +1. Okay? The important thing to know here is that the effective nuclear charge increases across a period. That should make sense to you, because magnesium, for example, which is next to sodium, has a very similar configuration, except instead of being 3s1, it's 3s2. So now it has 12 protons minus 10 valence electrons, which is +2. Okay? So it does also increase slightly going down a group, which we'll talk about a little bit more. You would expect that everything in the group would be perfectly +1. For example, like the alkali metals, you would expect all of them through this formula to have an effective nuclear charge of +1. And for the most part, they do. However, it changes just a little bit. It increases as you go down the group. Okay? So that is what effective nuclear charge is.